Pluto is a distant and enigmatic dwarf planet that was once considered a full member of our planetary system. However, recent surprising statements by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggested that this cold world is on a potential collision course with Neptune. But how could this happen, and what might be the consequences of such a colossal event? Are we witnessing an unexpected cosmic anomaly, or is there something else at play in this approaching celestial crash? Join us as we investigate the possible results of a Pluto-Neptune encounter. Pluto, once classified as a planet, now stands as a dwarf planet, yet it remains a topic of interest and study in the cosmic community. According to recent predictions by leading scientists, Pluto's orbit lies dangerously close to Neptune's, raising alarms about a potential risky impact between the two, which could pose a critical risk to Earth. But how is such an event even conceivable? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning that since its discovery in 1930, Pluto hasn't even completed one full revolution around the Sun. What makes Pluto's orbit even more curious is its highly elliptical shape, which deviates significantly from the nearly round orbits of the major planets. The eccentricity of Pluto's orbit causes it to wander greatly, and its inclination is set at 17 degrees to the ecliptic plane, making its orbit considerably more extreme compared to the other planets. This steep inclination and eccentricity add layers of complexity to its orbital path. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For roughly 20 years of each orbit, Pluto actually draws closer to the Sun than Neptune, which defies expectations based on their respective positions in the planetary system. This raises a natural question. Why hasn't Pluto collided with Neptune? The answer lies in the gravitational interactions between the planets. The investigation of Pluto's orbit began shortly after its discovery, as astronomers tried to understand its unusual path. Unlike the other planets, whose orbits lie mostly near the ecliptic plane, Pluto's orbit protrudes with its steep inclination and elongated shape. The mystery deepened with the realization that Pluto's orbit crosses Neptune's, yet their orbits do not lead to a catastrophic collision. The key to understanding this paradox lies in the three-body problem, a complex issue in orbital mechanics that involves predicting the motion of three celestial bodies based on their gravitational interactions. What keeps Pluto from crashing into Neptune is a phenomenon known as alpha libration. In the case of Pluto and Neptune, this means that whenever Pluto crosses Neptune's orbit, it is found no less than 90 degrees away from Neptune, creating a spatial separation that prevents a collision. Additionally, Pluto's orbit exhibits another safeguard, inclination libration, which refers to the upward movement of Pluto in its orbit. When Pluto comes closest to Neptune or any other giant planet, it is positioned above their orbital plane, further protecting it from a potential impact. Another crucial factor is the VZK oscillation, named after scientists Bond, Zippel, and Kai, who studied the interactions of gravitational forces between three objects in space. This oscillation helps explain why Pluto's orbit, despite its apparent irregularity, remains stable over billions of years. Although Pluto's orbit is chaotic in the short term, with slight deviations in initial conditions leading to significant changes over time, these eccentricities do not destabilize the orbit over long periods. Computer simulations in the late 1980s revealed that Pluto's orbit is maintained by a balance of forces, particularly the gravitational influences of giant planets like Neptune, Jupiter, and Saturn. These planets work together to ensure Pluto's orbit remains stable. In fact, for every 2 orbits Pluto completes around the Sun, Neptune completes 3, a relationship known as orbital resonance. This resonance stabilizes Pluto's path, preventing it from deviating into a more chaotic trajectory. Jupiter's gravity also plays a significant role in shielding Pluto from instability, and Saturn's influence contributes as well. Studies have shown that Jupiter's gravity alone is powerful enough to keep Pluto on a stable path for billions of years. These peculiarities are critical for maintaining order in the solar system, preventing potentially catastrophic events such as planets crashing into one another or being ejected from their orbits, which could trigger a cascading effect on other celestial bodies. In the case of Pluto, understanding its orbit provides valuable insight into the dynamic nature of the solar system. Even the most seemingly unstable orbits, like Pluto's, can reach a state of equilibrium through the intricate interactions of gravitational forces and orbital mechanics. The study of Pluto highlights the importance of ongoing observation and analysis to better understand our place in the universe. As we explore the depths of space, we are often confronted with the bizarre nature of celestial bodies, and Pluto's unusual orbit is a prime example of this phenomenon. The concept of orbital chaos, which refers to the sensitive dependence of a body's path on its initial conditions, is clearly illustrated in Pluto's case. Even small changes in Pluto's position or speed could significantly alter its long-term trajectory. This highlights the complexity of planetary dynamics and raises questions about the future stability of our solar system. Since its discovery, Pluto has undergone extensive study, leading to significant discoveries about its composition and behavior. One of the most intriguing aspects of Pluto is its surface, which is a complex mixture of ice, rock, and other compounds. The New Horizons mission, which flew by Pluto in July 2015, provided incredible data about this distant world. Pluto's surface features vast plains, towering mountains, and deep valleys. One of the most striking features is Sputnik Planitia, a massive heart-shaped plain made primarily of nitrogen ice. This region showcases a diverse array of geological features, including massive ice blocks and what appear to be flowing glaciers. These features suggest that Pluto might still be geologically active, despite its great distance from the Sun and extremely low temperatures. Pluto's atmosphere is another fascinating aspect. It is primarily composed of nitrogen, with traces of methane and carbon monoxide. Though thin, the atmosphere exhibits fascinating seasonal variations. As Pluto moves closer to the Sun in its elongated orbit, its atmosphere can expand and contract. During Pluto's closest approach to the Sun, some atmospheric gases may freeze out onto the surface, while as it moves farther away, these gases can sublimate back into the atmosphere. The interaction between Pluto and its largest moon, Charon, further adds to the complexity of the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This unique size ratio means that the two bodies orbit a point in space that lies between them, rather than Pluto simply orbiting Charon. This relationship adds to the gravitational dynamics of the region, influencing the orbits of other objects in the Kuiper Belt, a region beyond Neptune populated by small icy bodies. The Kuiper Belt is home to many other dwarf planets and potential impactors. It is considered a reservoir of ancient material from the early solar system, offering scientists a glimpse into the conditions that prevailed during its formation. Pluto's orbital characteristics may provide insights into the migration patterns of these distant objects, suggesting that interactions with larger planets played a key role in shaping their current orbits. Understanding Pluto's orbital dynamics has broader implications for our understanding of the solar system's evolution. The gravitational influences from nearby giant planets like Jupiter and Neptune can alter the trajectories of smaller bodies, including those in the Kuiper Belt. Such interactions can lead to changes in orbits, potentially causing collisions or ejections from the solar system. As scientists continue to study these interactions, they may uncover broader patterns governing the behavior of celestial bodies across the universe. The study of Pluto also raises philosophical questions about the nature of cosmic order. The decision to reclassify Pluto as a dwarf planet in 2006 sparked debates about what truly defines a planet. The astronomical community's definition, which focuses on orbital dominance and size, has led many to reconsider the implications of such classifications. This ongoing debate reflects our evolving understanding of the universe and underscores the need for a flexible approach to categorizing celestial bodies. Moreover, the potential for future exploration of Pluto and the Kuiper Belt remains an exciting frontier. Advances in technology and mission planning have led researchers to consider sending additional spacecraft to study Pluto and other objects with similar orbital characteristics. Such missions could provide valuable information about the primordial materials that formed our solar system and potentially offer clues about the origins of life on Earth. Finally, the study of exoplanets, planets beyond our solar system, intersects with our understanding of Pluto. As astronomers discover more exoplanets, particularly those in the habitable zones of their stars, the lessons learned from studying our own solar system may help inform theories about planetary formation and habitability. Pluto continues to capture the imagination of people around the world, fueled by its mysterious status and the stunning images returned by the New Horizons mission. Its unique position in the solar system invites a renewed appreciation for the vastness of space and our place within it. As we continue to unravel the mysteries of Pluto and the celestial bodies that share its corner of the universe, we are reminded of the awe-inspiring wonders the cosmos has to offer. Does Pluto's remarkable nature extend beyond its physical properties and orbit? It serves as a crucial case study for understanding planetary evolution and the dynamics of celestial bodies. The study of Pluto invites both scientists and enthusiasts alike to explore the mysteries that lie beyond our earthly bounds as we continue to explore Pluto and its unique characteristics. One of the most intriguing aspects is the potential for future discoveries that could further reshape our understanding of the solar system. For instance, recent studies have suggested that Pluto's surface may harbor more than just ice and rock. There is evidence that the dwarf planet could possess a subsurface ocean, hidden beneath its icy crust. While this notion was once speculative, recent findings from the New Horizons mission and further computer modeling have brought this possibility to the forefront of planetary science. If such an ocean exists, it could have profound implications not only for our understanding of Pluto's geological processes, but also for the potential of life in the outer reaches of our solar system. The idea of a subsurface ocean on Pluto challenges conventional assumptions about the conditions necessary for life. The presence of liquid water beneath an icy crust would offer a stable environment for chemical reactions, a key ingredient for life as we know it. Scientists are particularly interested in how such an ocean might be maintained at the incredibly low temperatures found at Pluto's distance from the Sun. One theory is that the ocean could be kept warm by tidal heating, a process generated by the gravitational interactions between Pluto and its moon, Charon. These interactions might create enough internal friction within Pluto to prevent the ocean from freezing completely. This dynamic could mirror the situation on other icy moons in the outer solar system, such as Europa and Enceladus, which are known to harbor subsurface oceans beneath their frozen surfaces. In addition to its geological and potential astrobiological significance, Pluto's relationship with its environment offers important insights into the broader dynamics of the outer solar system. The complex interactions between Pluto and its neighboring bodies in the Kuiper Belt provide a natural laboratory for studying the early solar system. Pluto's orbit, which is influenced by the gravitational forces of nearby giant planets like Neptune, can offer clues about how objects in the Kuiper Belt were shaped and moved over billions of years. These small, icy bodies, which are remnants from the solar system's formation, can shed light on the conditions that existed in the primordial solar nebula and the processes that led to the formation of the planets. Moreover, studying Pluto's orbit and the larger context of the Kuiper Belt may help explain some of the more unusual features observed in the outer solar system. For example, the existence of objects in highly inclined orbits, such as the scattered disk and trans-Neptunian objects, could be the result of gravitational interactions with large planets in the distant past. As we continue to explore Pluto and the Kuiper Belt, scientists are working to piece together a more complete picture of how the outer solar system evolved and how planetary bodies interacted to create the structure we observe today. Looking to the future, the exploration of Pluto and its distant neighbors is poised to expand our knowledge in ways we can only begin to imagine. Upcoming missions to the outer solar system, including potential flybys of other Kuiper Belt objects, could provide more detailed data on the composition, structure, and dynamics of these distant worlds. These missions will allow scientists to test hypotheses about planetary formation, the behavior of icy bodies in the outer solar system, and the conditions necessary for life to emerge. Each new discovery promises to push the boundaries of what we know and bring us closer to understanding the history and evolution of our solar system, as well as the potential for life beyond Earth. Pluto's enduring mystery continues to captivate both scientists and the public alike, drawing attention to the wonders that lie on the fringes of our solar system. The more we learn about this distant world, the more it challenges our understanding of what is possible in the cosmos. From its complex orbit and geological features to the potential for subsurface oceans, Pluto remains a compelling target for future research. As our understanding of Pluto deepens, one of the most exciting areas of research lies in its potential to shed light on the processes that shaped the early solar system. While Pluto itself is a small, icy world, it serves as a time capsule, preserving information from the solar system's formation over 4.5 billion years ago. The Kuiper Belt, where Pluto resides, is populated with many similar objects that are considered remnants of the primordial solar system. By studying Pluto and its neighbors, scientists can gain valuable insights into the conditions that existed in the early solar system, such as the distribution of volatile materials like water, methane, and ammonia. These substances are thought to have played a crucial role in the formation of planets and moons, and understanding how they were distributed across the solar system could help researchers refine models of planetary formation. Furthermore, Pluto's unusual orbital dynamics, particularly its interactions with Neptune, can provide clues about the gravitational forces that shaped the solar system. These interactions might have influenced the orbits of other bodies in the Kuiper Belt, potentially explaining the chaotic and varied paths of some trans-Neptunian objects. In this sense, Pluto acts as a natural laboratory, allowing scientists to explore the gravitational mechanics that govern the behavior of celestial bodies in the outer solar system. By better understanding these dynamics, we may also gain new insights into how planetary systems evolve over time, both within our solar system and beyond. The discovery of features like Sputnik Planitia, Pluto's nitrogen ice plain, further deepens the mystery surrounding the planet's geological history. The discovery of large, flowing glaciers and potential tectonic activity suggests that Pluto may still be geologically active, despite being so far from the Sun. This idea challenges our conventional understanding of cold, distant bodies and opens up the possibility that even the most remote corners of the solar system may still harbor active processes. Moreover, Pluto's potential to hold a subsurface ocean raises even more questions about the possibility of life beyond Earth. While the odds are slim, the existence of a warm, liquid environment beneath the icy crust could create conditions suitable for microbial life. This aligns Pluto with other icy moons in the outer solar system, such as Europa and Enceladus, which have also been considered possible habitats for life due to their subsurface oceans. If further exploration of Pluto confirms the presence of such an ocean, it could revolutionize our understanding of the habitability of icy worlds and expand the search for life beyond Earth. The study of Pluto also intersects with the growing field of exoplanet research. As astronomers discover more exoplanets in the habitable zones of their stars, the knowledge gained from studying Pluto's atmosphere, geology, and orbital dynamics could help inform theories about the formation and potential habitability of exoplanets. Just as Pluto's distant position challenges our understanding of planetary formation, the study of exoplanets pushes the boundaries of what we consider to be possible for planets that orbit distant stars. By studying Pluto in greater detail, scientists are not only unlocking the secrets of our own solar system, but also gaining new perspectives on how planets form and evolve across the universe.